Thank you. Hello to everyone in YouTube and Google Meet. Thank you for attending this seminar. And today we have a pleasure of having Professor Monika Moscibrodzka from Radboud University in the Netherlands. Professor Monika, thank you a lot for accepting the invitation for giving this talk. And Professor Monika is going to present the seminar, A Polarimetric View of the Edge of the M87's Black Hole. And before the seminar starts, Professor Rodrigo Nemi is going to tell us a little bit about Professor Monika. And from this point, I would ask everyone to, in Google Meets, to turn off your microphones and cameras. And the questions can be done to Monika during the presentation or after her presentation. And if you are following the seminar via YouTube, you can write your questions in the chats of the channel, and we will bring the questions to Professor Monika after the presentation. And now I pass the words to Professor Rodrigo.
Thank you, Reinaldo. So it is my great pleasure to introduce you to Professor Mościbrodzka. So Professor Mościbrodzka, she got her PhD in University of Warsaw. And then after getting her PhD, she did two postdocs, one in University of Nevada and then another one in University of Illinois. And now she's a professor at Radboud University in the Netherlands. And Professor Mościbrodzka, she had a leading role in the Event Horizon Telescope collaboration. She was one of the key figures behind the now iconic black hole shadow image that we all know, love, and cherish. And she is the leader. She has a very important role, a leading role in the polarimetric division of the Event Horizon Telescope collaboration, as she will tell us now. So, Monika, thank you very much for accepting our invitation for this presentation, and the floor is yours.
Thank you very much for the nice introduction. Let me share my screen, entire screen, I guess. So can you see my screen now?
Yes.
All right, and the full screen is also available?
Yes, the full screen.
All right, great. So yes, again, thank you so much. Obrigado. I don't know if I pronounced this correctly, for the invitation. And today I'm here to tell you about this new version of M87 image of a black hole shadow, a polarimetric image. And I will be speaking on behalf of the Event Horizon Telescope collaboration because this image, unpolarized and polarized one, is not a one human job. It takes a village to image a black hole, and not everyone on this picture, who participated in these discoveries, is on the picture. But there's really a lot of people involved in this, starting from data calibration, data processing, correlation of data, calibration, analysis, imaging, and then interpretation. So I would like to acknowledge all these people. And this picture that I'm showing you, that's showing the people that are behind these results, was taken in July 2019. So, 2 years ago, we already had these results that we presented in March this year. So it really is a couple of years of hard work of not only vetting these results, but, trying to make an interpretation of it. It took us 2 years, to make sure that what we're looking at is correct, and we understand what we're doing. But let me start from the beginning with some basic information. If you're not familiar with the Event Horizon Telescope, what is it? It's a VLBI experiment, very long baseline interferometry experiment, operating at high frequencies or at short wavelengths, to be precise, at 1.3 millimeter. So this is like a millimeter astronomy, millimeter VLBI. The left picture shows you Earth and shows the array, the VLBI array configuration back in April 2017. And it was April 2017 was a very special year because, you know, during this VLBI campaign, we collected data that let us, you know, allow us to make this first image of a black hole shadow in galaxy M87. This was, you know, published already 2 years ago. And this experiment, of course, you know, this is not the first millimeter VLBI observation made, but, you know, the number of stations involved in these observations, you know, already 4 years ago, you know, allowed us to collect enough spatial information about the source to construct the image or this kind of map. And this image, what are its basic properties? You know, you've probably seen it all over the news. It hit many headlines, but what are the properties, like the main features? Well, the diameter is for only 42 micro arc seconds. So it's a really, really tiny object on the sky. This is, you know, our current best, highest resolution instrument that we have. It can image object this small. And this 42 micro arc seconds corresponds to about 2.5 Schwarzschild radius. So, you know, this is what one would expect to see if such a ring is formed around the shadow of a black hole, around the black hole event horizon. And it's almost perfectly circular, and it has this brightness asymmetry, which is, you know, meaning that, you know, the ring is brighter on the south side. And this kind of asymmetry is very easily explained by effects such as relativistic beaming, relativistic Doppler effect. So it's probably a result of some kind of relativistic motion, circular motion around the source, around the black hole. And the ring, if you look at the scale, the plot, the light intensity on those plots is given in brightness temperature. So this ring has very high brightness temperature. So for millimeter observations, this means that this light is most certainly produced by synchrotron process, which is by relativistically hot plasma and magnetic fields. Okay, electrons, relativistic electrons are gyrating around magnetic fields, and this acceleration motion is producing radiation. And this type of light, as you know, it's intrinsically polarized, and it can be even up to 100% polarized, depending on exact electron distribution function that are in this, you know, accretion flow around the black hole. And you know, what can polarization maps tell us? You know, there are many questions that we have since we saw the ring. You know, is this emission produced by matter that is flowing into the black hole, or maybe a matter that is, you know, flowing out, or maybe it's just circling around there forever? Is the black hole spinning? You know, this is one very important basic question for high energy astrophysics. Are the supermassive black hole spinning? You know, for M87, we don't know yet, but we would like to find out. So maybe polarization can tell us, you know, how magnetic fields are twisted around this object, and maybe they can tell us something about the spin. And because you know, is this image going to change in the future? That also depends on you know, the magnetic field configuration in a ring. And finally, you know, how is this ring connected to a jet that we observe in M87 on you know, on larger scales at longer wavelengths. And before going into details of this particular observation and its interpretation, I would like to show you, start with this image and actually tell you precisely what are you looking at in this image. So here are two versions of the same polarization image of M87. So the left one, on the left-hand side, you see a scientific version of polarization map, and on the right-hand side, you see more like an outreach version of polarization map. On the left-hand side, the plot with the ticks, the gray is the light intensity, and this one is pushed to the background now. And on the top of that, you see ticks. These are so-called polarization ticks, and they tell you a direction in which electromagnetic wave electric vector is oscillating. So this is EVPA map, electric vector position angle map. And the tick color codes the what fraction of light is polarized, and the tick length basically is proportional to polarization flux in polarized light. So this image shows you that only south and west portion of this ring is polarized, and the fraction of light that is polarized is maybe up to 15%. So this is very low, as you know, from one would expect to see in, you know, from hot relativistic plasma in this kind of relativistic source. So that's kind of surprising. Why is it, you know, this polarization so low? But here I wanted to tell you that, you know, you see just few ticks on the top of this gray image. It's because in radio astronomy, in radio polarimetry, we usually plot a small number of ticks on the top of the total intensity maps, because polarimetric data, you know, they have very similar resolution to total intensity data. It's the same data. So in VLBI, one usually plots few ticks per beam size, which here is about this 20 microarc seconds. This is the nominal resolution of EHT. And the picture on the right depicts this polarization using so-called line integral convolution method, and where you see a brush strokes, and these brush strokes basically follow the electric vector position angle vector field. So because of the way of this type of visualization, you know, this image appears like it has more details, that it has maybe higher resolution, but that's not really the case. This polarization data, it has the same resolution as previously. So, you know, it's just give you this, may give you this impression that, you know, you see more, but that's not really the case. But I think the most important here is to mention that what you see looking at here, those lines, those EVPA fields, this is not yet magnetic field. This is just the direction in which the light wave is oscillating. So, you know, we have shown this right-hand side image in our press release in March, earlier this year. And we said that we are now mapping magnetic fields, but that's not yet a map of magnetic field. This is just polarization map. And for synchrotron radiation, it's always, you know, the rule is that you would have to just rotate the ticks by 90 degrees to obtain the position, the direction of magnetic field line. But because this emission is coming from very, deep gravitational potential of a very massive object, a black hole, where the space-time is bended, plus there's a lot of plasma in there. You know, the interpretation is not that simple. So we cannot just, rotate them by 90 degrees and say, okay, that's magnetic fields. No, this is done. The interpretation is done via rather sophisticated models. So in the first part of my talk, after this short introduction, I will tell you about the observation, and then I'll tell you about, how we interpret this type of images. Okay, observation. So which data have we used to create this new image? This is the same data that has been collected back in April 2017 during the first real, EHT campaign. In that year, we observed M87 for 4 nights or 4 days, because millimeter astronomy, we can also observe during daytime, actually. So this is the array, elements involved. And this is actually how M87 polarization looks like in a UV space. In other words, in a Fourier domain, because, Event Horizon Telescope is an interferometer. So it picks up Fourier components of the image on the sky. So each point here on this 4 plots, it's one spatial Fourier component of this image. And this is what EHT sees in polarization. The color codes here fractional polarization in UV space in a Fourier domain. And this interferometric polarization actually can be higher than 100%. That's totally normal. But here it's evident that, you know, M87 is rather weakly polarized source. It's already visible in the data itself, even without imaging. And you can see that if you compare day to day, that, you know, there are some small variations in polarization from day to day, but not, the source doesn't change dramatically, okay? And because M87 is a compact source, we know that now, we see just a ring in there. It's also the best source that we have for any polarimetric calibration. And given that it has excellent, you know, this coverage, so-called UV coverage. And, you know, I will be talking about calibration a little bit during this talk, because this is like a very important part of this story. I will tell you later why is it important to talk about it. All right, so how do we got from this data to images? Well, you know, to make images from VLB data, we have to really deconvolve it from, there's a lot of noises, yeah, in this data, systematic errors, you know, and other type of errors. We have to, one has to have very good understanding of this array, and, you know, it's a very heterogeneous array. Each antenna is different, and one has to really know everything about those elements and about observing conditions during, you know, a campaign that may always introduce some biases. And in particular for what's important for in polarimetric imaging, just like in all standard VLBI polarization that, you know, has been done for last 40 years or so for blazars and AGNs and so on, and many other sources, there is polarization leakage that we have to deal with. This polarization leakage, it's a property for each antenna in an array that can make unpolarized source look like polarized one, for example. And usually these leakage terms, these calibration terms, are of the same order as the source polarization. And so, you know, this is like an imperfection of each antenna receiver that has to be estimated from the data in sort of like an iterative way during this images process. And this is actually was one of the largest difficulty in our analysis to disentangle actually this instrumental polarization from the source polarization. And I will, yeah, I will devote some time to explain you this a little bit more, because, you know, these calibration terms have some impact on our images. And at the end, you know, our image really is very sensitive to what do we do with this calibration. And the first attempts, of course, to make polarization image came very early, as I said, nearly at the same time when we published total intensity maps back in 2019. And here, this is how this preliminary result look like. This comes from, these are three examples of total intensity maps on the left. In the middle, you see polarimetric map. And on the right-hand side, you see those leakage terms. These are the calibration terms for three chosen elements. The red points are, for example, calibration terms for LMTs, the large millimeter telescope in Mexico, for example. But already, you know, this three plots here, 3 rows, shows you results, preliminary results from 3 very well vetted softwares. EHT imaging, for example, is developed by Andrew Shale. This is the regularized maximum likelihood method that has been developed for this kind of millimeter astronomy kind of recently, really. PolSolve, that's developed by Ivan Marti Vidal. Maybe some of you know him. This is based on CASA software. So, you know, CASA is now like a standard tool in radio astronomy. So, you know, we're not using any sophisticated new things. PolSolve is something that is available, right, to the community. I mean, CASA is available for the community. And LPCAL is actually a standard old VLBI machine that is also used for years. It's a command line in apes software. So yeah, so one can recover these results, you know, using really tools that we already had at hand. Right. So already all preliminary polarimetric maps looked very close to what we have presented, you know, finally recently. You can see polarization, the south part and the west part of the ring is only polarized. And you see this, you know, polarization up to 15% at most. And there are some small differences between these different softwares. Well, that's just due to slightly different calibration that you see on the right and peculiarities of each of the software. And yeah, but you can see that they are already quite consistent. And what's the next step? As in all EHT process, is testing those algorithms. So since each of them have, you know, 3 parameters, for example, field of view, resolution of your image, data weight you can put into your imaging process, but I'm not talking into detail today. But you know, what you want to know is what are those best values of those 3 parameters to use to image M87. So in algorithm, you know, testing phase, we usually create a synthetic data based on some model images that you see on this slide. So we will try to make these mock images as diverse as possible. You can see this type of models are quite different. Some of them are quite complex, some of them are simpler. We then convert these images into interferometric data by basically doing forward Fourier transformation of those images, 2-dimensional really Fourier transformation, and we corrupt the synthetic data by instrumental noises that we know of, and then we use this mock data and we try to recover the truth images. And this is a typical way of doing this, you know, also total intensity images, okay? This is always done in a similar way. And here, on this example, I would like to show you that how well different imaging methods can recover this kind of synthetic image. I will just show you one example. Eventually, we have used not 3 methods for polarization images, but actually 5 reconstruction methods. And because, you know, because polarization is more difficult than total intensity, and, you know, because of this additional instrumental polarization noise, polarization leakage, we have, you know, eventually implemented 5 methods for making polarization maps. So we were extremely careful, you know, it's almost paranoid, yes. But because these 5 methods are all very different, the 2 new ones that I'm showing on this slide is DMC and TMIS. DMC is developed by Dom Pesce in CFA and TMIS by Ever Broderick in Perimeter Institute. But, you know, because testing 5 methods takes time, okay, and this is also the reason why it took us so long to release these results. But all these tests, synthetic data tests, allow us to pick a fiducial set of imaging parameters per method to make so something that we called a fiducial image. So here I'm showing you final fiducial images from these 5 different imaging methods when working on the real data, in this case, not synthetic data. This is real M87 images from April 11, from the last day of observations. So as you can see, there are still some small differences between these images. It's just due to, you know, peculiarities of each algorithm, and there is no way to make them even more similar. Okay, this is the best we can do. And, you know, also all these fiducial final images from each method look very similar to what we saw initially. Again, all 5 methods show, you know, southwest part of the ring being polarized and, you know, this low polarization of 50% at most. And EVPAs, the polarization pattern is always sort of like oriented in or forms this kind of azimuthal pattern. The EVPA field is almost, along the ring, okay? Maybe there's some small angle there. So it's almost azimuthal, yes. So what we show in our press release is method averaged image. So we took 5 fiducial images per method and we just stacked them together, and this is what we show as a final image. And we have chosen to show April 11 as our press release image because this is a day on which we have collected the highest number of data has been collected on this day compared to other days. And the top panels show you, again, the more scientific version of these maps, and the bottom panel is just for outreach. Let's focus on the top panels, the scientific version. One can immediately notice that this polarization structure, well, it's similar, but you can see that clearly there's a difference between the first 2 days and the last 2 days. So there is some signature of the evolution of this polarization map between the pair of days at the beginning of the week and at the end of the week. This is very consistent with what we have saw 2 years ago in total intensity maps. Total intensity maps already look slightly different on April 5 and 6 compared to April 10 and 11. So, this is a signature that, something is moving in the source, and it looks like it's the magnetic fields are moving in the source and changing its appearance. All right, so now the final step in this polarization imaging is to assess very carefully how stable are those polarimetric maps against instrumental leakage. This is how the instrumental leakage looks like. These plots, they're kind of busy. You don't have to understand what these D terms are really, but these are calibration terms per each antenna. They are determined during a polarimetric imaging process. It's an iteration process always. And, you don't have to really understand what exactly they mean, but you see that, all these points with different colors are sort of like consistent with each other. But, there is some small spread. And leakage, it's not a variable, it's a fixed property of each antenna that is fixed in time. It rather shouldn't change in time. So we had to check, how our fiducial maps, the final maps, change within this spread of calibration. So these calibration terms are also given in percentage. So, you can see that this polarization, instrumental polarization is comparable to the source polarization. So it was really very important to check, how the image depends on these D terms. In case, if we make small mistake in calibration process, what's the impact on our map? So how this was done? Well, we have done a Monte Carlo simulation. So this was another extensive exercise because for each method, we have produced 1,000 fiducial polarimetric maps with leakage that was slightly off. So these distributions that you see here, the medians and the standard deviations are estimated from this fiducial leakage obtained for all epochs of observations per method that you saw on the previous slide. So here's the example of polarimetric image stability against this different leakage calibration for one example pipeline, each imaging pipeline. So this movie that you see here shows you a series of 1,000 polarimetric images of M87 with slightly different calibration. So if we made some small error in our calibration process, this is how the image will change. So it just shows that calibration really doesn't really matter. It doesn't really matter. The main feature of the image, the polarization level and polarization location on the ring and the shape of it does not significantly change. And we have repeated this type of Monte Carlo simulation, Monte Carlo imaging for all methods and all days. So these results for other methods look very similar to this example shown here. But I wanted to tell you about this because it's very important to maybe say that there's no like one final M87 image. There is actually 20,000 final images, 1,000 for each of 5 methods and for 4 days. So, you know, what we choose to show at the end, you know, is just one of those images or some kind of average. Okay, so this is the message maybe here, that EHT collaboration has, you know, is producing a lot of this kind of maps, not just one. Okay, how to quantify all the images and how to describe them? Well, this is a very important question because, you know, in the next part of this talk, I want to explain to you how do we compare this kind of maps to models to infer some information about magnetic field structure or plasma condition. This is what we finally want to find out, right? Eventually. So we have actually used 4 polarization so-called metrics to describe those images. So the easy one is the net fractional polarization of an image. It's easy to calculate. You can see a definition of it in the first equation. The second one is so-called mean image polarization. It's defined a little bit differently than the net polarization. It's a mean polarization weighted by total intensity. And what this measures is actually an order in polarization maps in image. And the last metric, so-called beta-2 function, this was basically introduced by Daniel Palumbo, who came up with a decomposition of complex polarization, where P complex polarization is Stokes Q plus I Stokes U, into this kind of azimuthal modes. And they have found out that actually mode equal to are best when it comes to discriminating different models. So this beta function, you know, it's a complex number. It has amplitude and phase, and one can use both to actually discriminate between different maps. And the plot that you see here, the 4 plots, these are of course synthetic polarimetric maps based on general relativistic magneto-hydrodynamic simulations of M87 that show, you know, how these 4 numbers, how different they are depending on some main feature visible in the maps. So you can see that the top panels more or less look like, you know, observation of M87. So you can see more or less what are those numbers for this type of maps. But these are models. And now what do? We can calculate this kind of metric distributions using our samples of 1,000 images per method with slightly different polarimetric calibration. So this is how this distribution looks like. So the top ones, you can see possible fractional polarization of M87, distribution of polarization of M87, net and mean, and the bottom histograms shows you how this beta function amplitude and phase look like for the real M87 image. You know, this distribution of this metrics that encapsulate, you know, all the uncertainty from polarimetric calibration. And we have done this, we have calculated this kind of distributions of metrics for each method separately, you know, to be conservative. And we do that for each day of observation separately. So now I will move on to the second part of the talk. I hope I still have some time. I'll try to maybe go fast through this. All right, so you know, we want M87 model, a good model that fits the observation, to recover the 4 metric of the image produced by EHT. which is not a single number now, but it's just you know, a range that encapsulates the uncertainties in imaging and calibration errors. So EHT measures, so we have these 4 metrics from EHT. EHT measures only linear polarization of M87 ring, but you know, synchrotron emission can be also circularly polarized. Where do we get circular polarization from? Well, we have additional observations from ALMA array, and this observation, simultaneous observation, tell us that M87 core almost have no circular polarization. We still don't understand fully why is it so, but it's basically the circular polarization is less than 1%. So we use this additional constraint as you know, an additional constraint, right? Because our models include all polarization, so we just want to make sure that the circular polarization is not, you know, over some upper limit. And well, M87 is low luminosity AGN, and we believe that you know, accretion in this kind of sources that have low luminosity in terms of Eddington luminosities proceeds in form of ADAF, advection dominated accretion flow. So these accretion disks, you know, are very hot, relativistically hot. They are geometrically thick and optically thin. This is a numerical model of such an accretion disk. The orange color is the accretion disk, and the white cones. This is an outflow, a jet, a boundary of a jet, really. So jets are naturally produced in this kind of simulations. And the lines, the spaghetti lines, these are magnetic field lines that are being twisted around the black hole, you know, by accretion. And so we have a large library of this kind of simulations for M87 already from 2 years ago. This is a polarized version of it, or rather a sample of polarized snapshots from the library. So on the top of the total intensity here shows in orange, the ticks represent linear polarization, and we consider 2 types of models for M87: SANES and MADS. In SANE, which stands for Standard and Normal Evolution Accretion Disk, the disk is rather turbulent, and MADS are, you know, magnetically arrested disks. MADS have more powerful jets in general, and in this kind of disk in general have a quite dynamic. They have a power to sometimes even stop accretion because of very high magnetic pressure. And we have picked 200 snapshots from each of the simulations that we have in a library, and we have basically imaged this type of simulation as 3 viewing angles, and we have also assumed that the models may contain 2-temperature plasma. You know, after all, we are considering inefficient accretion flows where plasma, electrons, and protons can thermally decouple. You know, this is usually some additional physics that has to be incorporated in this kind of accretion disks that have very low densities. You know, they are effectively made of collisionless plasma. So we have a 2-temperature plasma model where we change these 2 parameters that we call R high and R low. These 2 parameters control, you know, how changing of coupling, thermal coupling between the 2 species, the protons that do not radiate and electrons that radiate. We see emission from electrons. And finally we have considered models of accretion disk onto a non-spinning black holes, but also on spinning black holes, including cases where the disk is rotating in the opposite direction than the black hole itself. So eventually we have 72,000 snapshots to compare to. How this type of images are basically created? Well, this is done via so-called ray tracing simulations. So we post-process MHD simulations with radiative transfer codes, ray tracing. So we have a polarized version of it. What do these models contain? They include, these are the equations that are involved. Geodesic equation is being solved, and along each geodesic equation, for each pixel in our image, we basically solve a radiative transfer equation for fully polarized radiation. This equation includes plasma emissivity, but also plasma absorptivity, which is low but not zero, you know, at 230 gigahertz, 1.3 millimeter that we observe at. And another two very important effects that are included is the Faraday rotation and Faraday conversion. So these two effects may affect polarimetric maps that have to be incorporated into models. Faraday rotation, it's plasma effects that cause rotation of the EVPA vectors in a colder plasma, and Faraday conversion converts linear polarization into circular polarization. So if there is some huge conversion on the way, it's possible that, you know, some polarization is disappearing and just being converted into circular polarization, and we won't see it in linear polarization map. So all these effects are included, and just to give you a sense how different magnetic fields configuration a black hole look like, here are example which shows polarization EVPAs patterns produced by pure modes of magnetic fields. So purely toroidal field will appear as a radial polarization ticks. Purely radial field in the middle will have show up as a purely azimuthal ticks, and vertical fields threading the black hole will basically show this kind of twisted azimuth, nearly azimuthal pattern. And this twist of polarization vector is due to two effects: gravitational potential, parallel transport of EVPA vectors in strong gravity, but there's also Doppler effect involved here. And these three examples are probably quite instructive, but they are, this kind of semi-analytic models are missing three important things. First thing is missing that probably in reality what we see is a mix of these basic modes. And the second thing that simple models miss, but GRMHD models have, is this Faraday rotation. So we found that in GRMHD models, polarization pattern can be distorted by internal Faraday effects, such as Faraday rotation that happens in the same location as the emission. Faraday rotation can non-uniformly rotate maps and even scramble the map. Then such scrambled maps, when you blur them to nominal resolution of EHC of this 20 microarc seconds, will be depolarized. But this is kind of consistent with what we see in M87, you know. It's very weakly polarized source, which is very strange for us, for this kind of, you know, source with a jet. So this is actually our current interpretation that, you know, the idea is that the ring is mostly depolarized because of such strong Faraday effects, internal Faraday effects that are happening in the ring. And our GRMHD models include that. And the third thing that is not included in the simple models, but is included in GRMHD simulations is the variability. All GRMHD models are variable, and because we see variability in the source, we rather use these dynamic models. So within one model, snapshots are different at different times, can look quite different, and as visible in the movie. And detailed explanation of this kind of movie is quite difficult. So we have 72,000 snapshots like that for different models. We calculate image metric per each, and this is how GRMHD model library looks like in terms of image metrics. Here we made a division into histograms into MADS and SAINS on prograde and retrograde orbits, and the allowed ranges that are allowed by EHC polarimetric images are marked by vertical blue shaded regions. So how do we decide which model is consistent with M87 observation? So we came up with two scoring methods. So I will just probably have just time for one because I would like to finish soon. So the first, this simultaneous scoring method, we simply rule out models where none of these 600 snapshots in a given model can simultaneously satisfy all the image metrics plus circular polarization. And this plot shows you a number of passing images per model type. This is marginalized over this electron-ion coupling ratios. It turns out that only a very small fraction of images can satisfy all constraints. So we have only 73 out of the 70,000 snapshots actually satisfy the observational constraints. Interestingly, we see that actually magnetically arrested disks are rather favored by this observation, but saints are not ruled out. We still find turbulent accretion disk consistent with observations, but only just few of them. And very interestingly, MATs are favored, but models that have more than 5 passing images are those MATs which have kind of low spins, which is kind of unexpected because we all expect M87 to have large spins, right? It has a very powerful jet. So here, how models with passing and failing simultaneous scoring looks like. The top one, the two top ones, the first top one is one of those passing sane simulations, and the two right ones are MADs. And the bottom one shows example of our failing models. Models will fail if they are too polarized or too depolarized, or if they have wrong orientation of EVPA. All right, so I think it's time to summarize. Oh, I don't know what happened here. Can you see? Okay, I think something got frozen. All right, so what are the new lessons learned from this polarization imaging? For the first time in human history, I'm sorry, I think my screen is frozen.
Yes, your screen for some reason got frozen indeed.
Yeah, there was some big movie here. Okay, I think I'll just say it in words then. Okay, so what are the new lessons? For the first time in human history, we have, attempted to constrain geometry of magnetic field lines close to the event horizon. So this has never been done before on these scales, on, so close to the event horizon. So, it's a lesson on its own. And here I wanted to show you a movie of one possible scenario of how magnetic field lines may look like close to the black hole. They're shaped in sort of like a tornado shape. And the second lesson that we have, I think this is completely frozen. I'm so sorry about this.
Maybe, excuse me, if you stop sharing and start sharing again, maybe it will correct.
All right, No, I think it's my presentation is dead, basically. I'm so sorry. I'll just finish it.
No problem.
Without it, maybe. I cannot even see you anymore. I'm sorry for that. All right.
No problem.
All right, the second lesson, we have now actually much better constraint on how much matter is falling onto the black hole per year. In units of solar masses, that would be 10 to the -3 solar masses per year. This is about 1 Jupiter mass swallowed per year by this black hole. And this black hole is on starvation, as expected. For low luminosity AGN, but this M dot near the horizon is actually much lower, like 2 orders of magnitude lower than mass accretion rate estimated at the Bondi radius in M87 from, for example, X-ray observations, from Chandra observations. So these are like a very old results from Tiziana Di Matteo back in 2003. And the third lesson is the jet power. The estimates now is that near the black hole, the jet power is between 10 to the 42, maybe 10 to the 43 ergs per second. And this jet power is sort of like on the lower end than what is expected to be in M87. There is also, at this moment, there's no spin estimate for M87 black hole. This is because in generally, polarization it turned out that it doesn't really help with spin estimate. Polarization, as I mentioned, is actually turned out to be way more sensitive to plasma, to temperature structure of plasma because of those Faraday effects that kick in. All right. And finally, I don't know, this is really annoying. All right, so finally, just to summarize, I wanted to say that, Event Horizon Telescope just published near horizon information for the second time. First polarimetric images on these scales. Polarimetric images put much stronger constraints on any theories which will try to explain the ring emission or jet launching theories, because we are imaging a jet launching region really. Our scoring model scoring procedure disfavors most of GRMHD simulations right now. It's only less than 1% of them passes. And we have now much stronger constraints on mass accretion rate on M87. Polarization fraction is set by Faraday rotation in emission region, and the EHT, the polarization seen in EHT is probably a result of some beam depolarization. And this azimuthal pattern that you see on the plot requires some significant poloidal, either radial and or vertical magnetic field being close to the black hole. So this means that magnetic fields in accretion flow are probably they are dynamically important. And of course, models that we consider right now are not complete. They don't have there's still a lot of physics missing, like radiative cooling. We have not considered MHD models that are misaligned, tilted disks. And we have not done any extensive study of particle acceleration into a power loss, for example, and what kind of impact would that have on polarimetric images. And all models that I've been telling you about today are built in standard theory of gravity, in the standard GR. And at this time, we have not attempted to interpret the variability that we see in polarimetric maps. But the bottom line here is that we can still explain this image using the models and the physics that we know of. There's not, in some sense, no like something super unexpected here. Yeah, there's again no surprises. And the future observation will tell us much more, because they will be done at wider frequency band. They will allow us to also do rotation measure studies, circular polarimetric maps, and study variability. And eventually EHT polarization in combination with multi-wavelength observation will even be more constraining for all models. And now the question is how Sagittarius A-star, our second target, will be seen in total intensity and in polarization maps. So this is something for the future. I think I'm going to finish now. I think I went well over my time, so apologies for that. And thanks a lot.
Well, thank you a lot, Monika, for the very interesting talk and for sharing your research. We see it's a very careful study you are carrying out. Thanks again for the clear explanation. And now we'll open for the questions and for the discussion. The first one, Elizabeth, please. Go ahead.
Hi, Monika. Thanks
Hi.
for the, how are you doing? Thanks for the wonderful talk. And actually, I have several questions, but I will try to be more focused on a few ones. So, the fact that there is this strong Faraday decorrelation, isn't this in evidence that probably the measurements of the local polarization around the accretion disk is highly affected by the surroundings? And because we are looking at this accretion edge-on, face-on, right? So probably it is being affected, and therefore this would also affect on the value, the intensity of the magnetic field, which is surprisingly small, considering that we are very close to the source. And in this sense, what one can say because this depolarization may be an indication that the intrinsic magnetic field is really much larger and much more organized. So what are your comments on this? And also I have a technical question regarding the constraining, because of course this is rather model dependent, right? You have to run several GRMADD with a radiative transfer and then constrain and try to converge, doing also Faraday depolarization measurements. So to what strength can we really, rely on this result, in the sense that, okay, in the simulations, what was the intrinsic magnetic field that you were using, and what was the resulting magnetic field? Because, okay, from the measurements, it's around 10 Gauss or so, right? The conclusion. But what was the intensity of the magnetic fields, the initial conditions, when, in order to set up the simulations and then do all the polarization, including matter around? How do you did you guys deal with the surroundings, I mean, in depolarization effect?
Yeah, so all this, I will start from the second part. So all the simulations start, this is it's very standard. It all starts with a torus. These tori have different sizes depending on the model. In the same model, you start with a smaller torus. In magnetically arrested disk, you start with a big torus. It's like we always start with some fixed reservoir of matter rather close to the black hole. And the models are usually relaxed, maybe within 20 gravitational radii from the distant-wise from the black hole center. What's happening beyond? It's just, we just don't know, what is the structure of accretion disk outside, on larger scales, right? So yeah, I agree with you. There is some kind of uncertainty introduced by this in these models themselves, right? But this is the best that we have right now. These are the best accretion disk models for this kind of sources that we have now in astronomy. There's nothing better. So we decided that it's better to use the best model that we have. But we are absolutely aware that these models are not complete. And maybe in the future we're gonna have to build something more. It's definitely so many other effects that are not just initial conditions. There are many effects that we still don't include, right? Like I said, particle acceleration, cooling, maybe some thermal conduction, maybe it's not hydrogen plasma falling in, but some other species. This is still yet simple.
And the fact that
in terms of physics, we don't have Compton cooling, we don't have radiative cooling at all, although it may be important for M87. We still don't know how to couple things that are happening on plasma scales with these global models of accretion disks. There is a big gap, so we try to compensate that by introducing some parametrization to encapsulate all these different scenarios. But like I said in my summary, we sort of like, we know that it's probably the models don't capture like everything, but like I said, this is the best that we have right now. Like, this is the best that we astronomers have in the current moment. So we rather compare the observations to these best models that we have, rather than there's nothing else we can do at this time.
Yeah, that's true indeed. But still, the results are quite surprising. I mean, the intensity and the high degree of depolarization may be a hint that the surrounding effects are not. I mean, the surroundings, the immediate surroundings.
That's true.
Not only specific plasma effects or radiative effects you know, like collision glass.
Yeah, but we do even have evidence in the data itself that this is happening. We do see a non-zero rotation measure in this data.
Yeah,
it's on the edge of detectability because the bandwidth of EHC is still too small to have reliable measurement. But we do see in those maps themselves that at slightly different frequency, the image is rotating in one part. So we see a signature of some rotation measure. It may be happening, you know, in the source itself, but also a little bit in some rotation screen, you know, rotation measure screen a little bit outside of the source. And there's no way we can even estimate where the screen is, what are its properties, and so on. We need more data to actually figure this out like completely,
But great, anyways. Thanks a lot.
No, please, Juan.
Yes, can you hear me?
Yes.
Thank you for a very nice talk. I have a question. I have two quick questions. The first one regarding let me see if I correctly understood the polarization, the polarization maps that you obtained from the observations looks like a quasi-stationary, or this is because you took the average. This is what you said from different models. And whereas the models that you use to interpret them looks like a very variable in the shape of the lines. So is this something expected because of a numerical aspect, like something that you have to wait your simulation to be stable for a long time, or this is a very big uncompatibility?
No, it's just a matter of different time scales, because in M87, the dynamical time scale at the event horizon is about 9 hours. So the source is not expected to change over one night. So within 1 week, you know, the expectation is that it will change a little bit, but not that much. And the movie from models that I have showed you have been evolved for much longer. For like in terms of, you know, wall clock time, it's months, maybe even up to years. So, you know, GRMHD simulations are evolved for a long time. And the movie that I've showed you, it covers maybe 1 year. That's why it looks more variable. Observation is just 1 week, which is very short for M87. We don't really expect much to change over 1 week.
Okay.
Does it answer?
Thank you.
Is this okay, clear?
Yes. The other question is regarding the capabilities of the EHT facility. So with the resolution that you were discussing, is this able to, changing a little bit of topic, is this able to spot other, let's say, other sources to confirm or rule out the presence of supermassive black hole binaries in close orbits? Is this, can you comment on this?
Yeah, that's actually the goal, like a scientific goal of this future array. Probably this is already being explored by many people, and yeah, this EHT can be used not only to image event horizon, but also, you know, watch many other objects. Yeah, and that also includes the binaries, but it's not really clear whether they exist, right? Or where are they? So you would first need to know where to look.
Well, there are some candidates, but the thing is the definite answer would be provided by the observation. That's why my question.
Yeah. Well, the thing is that, you know, we are observing at 1 millimeter. So this, if these binaries exist and if their separation is of 20 micro arc seconds or larger, they also have to, the third condition is that they have to be bright at millimeter waves. So, you know, maybe that also depends in what sort of like evolution state are they. Are those two black holes in the binary system, you know, bright enough to be visible at this frequency? You know, how much do they accrete? You know, because I don't know the exact physics what's going on there, but, you know, if they have some mini disks around them, I don't know what kind of disks are those, but, you know, maybe they shine mostly in optical band, on in X-rays, not so much in radio. So you have to make them also bright in millimeter waves.
Thank you very much.
At least one Jansky or something of the order of Jansky.
Next question by Antonio Mario.
Yeah, thanks, Monika. Very nice talk. We enjoyed it. I work in optical and infrared polarimetry, and 15% for us will be fantastic. It'd be great, but
okay.
but it's kind of small, perhaps, for synchrotron, I guess, from your standpoint. Okay, I have how many hours we have for questions? No, okay. So how do you estimate the polarization signal to noise? Is that from the stability of the D term that you were talking about? Is that from the possible variation in the D term correction? Is that where you get the accuracy of the polarization signal? Does that make sense?
That's right. That's right. We deconvolve this instrumental polarization, and then you get some noise level, but that's small. Actually, the signal to noise here is rather high.
Okay.
As I show you in this one movie, it's more or less 15. And I had some other, I didn't have probably the plot here. Yeah.
So
yeah.
No, I was just curious, since
we are pretty certain of this number.
No, yeah, sure. I was just curious where you would quote the signal to noise from the usual, noise from the antenna and stuff like that, or something else, right? Yeah.
No, it's mostly the D terms, because they can be of the order of few percent, and these are the most important, I think, uncertainty here for the polarimetric maps. There are other, uncertainties, probably some systematic errors, but these are minor.
Okay, right. The geometry that you were, maybe it was in the movie that you were not able to show, but are we? So I'm still uncertain of what are we looking at? Pole on onto the disk. Is that what it is? What's the inclination angle under which we are looking at the disk? It wasn't clear to me.
Yeah. So all these models were computed at viewing angle of 20 degrees, where 0 degrees corresponds to face on, looking along the black hole spin. So all these models are almost face on, like we see disk or whatever rotating in the plane of the sky. So it's very low. It's M87 is very close to like a blazar-like source. It's not a blazar, but it's close to blazar.
And the Doppler effect that will cause the brightening there, is that because of so essentially the rotation? That's what it is, rotation of the disk. Okay, got it.
That's right. That's right. The matter around close to the black hole is rotating almost at the speed of light, and that's the major component here.
Right. The circular polarization in synchrotron radiation, you kind of expect it to be very small, right? The circular polarization from synchrotron, do you not?
We expect some non-zero, but it also depends on how cold the plasma is, because you can produce circular polarization in two ways in synchrotron emission, either intrinsic emission or you can have Faraday conversion. In relativistic sources, Faraday conversion can be large. And then, the circular polarization can rise up to like 2%. That is already a lot in our terminology. But typically, it's less than 1%.
Okay, right. Yeah, okay. Because I thought that, when you average over a beam, the electron radiation over a beam of, your beam, right? Measuring beam, it would kind of tend to cancel the circular polarization. So you would expect it to be very small, but I guess.
Yeah, there is this canceling. This canceling also works for circular polarization, indeed. But there are, papers being written that actually, if you look at this kind of source from this kind of angle, if there's a certain geometry of magnetic fields, and especially this rotation, actually the polarity of the image is same everywhere.
Okay, all right.
So, but these are the typical numbers,
Okay.
2, maybe 1%.
The other thing
maximum.
The other thing is I was surprised to see, to see the Faraday rotation at such high frequencies, because you would expect, again, you know, traditionally to be very small, right? But
yeah, but M87 and also Sagittarius A star in the center of our galaxy are very special sources.
Okay.
So the two sources that have the highest rotation measure on the sky.
Right.
It's of the order of 10 to the 5, you know, radians per meter squared.
Okay.
These are the extreme on the sky. So,
Okay.
you know, there's another blazar, I think 3C84 maybe.
Okay.
It's also this kind of, but the Perseus source, the Perseus. These are extreme, yeah. Okay. So, it's very high rotation measure. Right. It's not like magnetic fields in our galaxy, which is really low.
Okay, so for a non-relativistic astronomer, so this 9-hour time scale that you quote comes from is that some what's that variability from? Is that essentially from rotation? Is that what it is, or something else?
Yeah. If you have a blob and you put it at the innermost circular stable, last stable orbit around the black hole, you know, it will take 9 hours for the blob to go around.
Oh, okay.
There's some fluctuation in the disk, and you see some variability. You know, you would expect some changes to see, you know, on this type of time scale of the order of this 9 hours.
In the object frame of reference, right? Yeah, right. Okay, got it. Right? Not the observer.
That's right. Yes. What observer sees is different. Yes, in GR and all special relativistic effects.
Okay.
And lensed images and double images. You know, it's all different. Yeah.
Okay, great. Thank you very much again for the talk.
You're welcome.
Okay, I have a few questions. I think they are very simple. Probably the ones who have intuition in the subject to be something very simple. I have a doubt why there is no polarization in the north part of the image. Is that the polarization is proportional to the light intensity in the system, or
well, polarization is a part of light. The same, it's the property of light that we see. Yeah, I think this is a really good question, and we think that this is more is depolarized from there. Like this is also either some Doppler effect, or it's just basically, you know, this region, the emission from that region, you know, is a little bit away from us. It's maybe behind a little bit stronger Faraday screen. It's not really clear what the answer is. Yeah, but it's indeed it's more depolarized.
Because it also appears in the models you prepare, right? The models you synthesize. And,
it's very difficult to explain those models as well, because so many effects are happening along every single line of sight, along each ray, you know. Emission, absorption, and these are different in all Stokes parameters, plus these Faraday effects that interchange the polarizations, plus the Doppler effects. You know, it all comes together to form this kind of image. So it's not really clear how to explain this, like precisely, you know. I think there's a lot of work to be done yet in this area to actually, you know, understand every single detail.
Yes. And is it relevant, the effect of the resolution in the depolarization? I mean, because I don't know how fast in space the magnetic field is changing the direction, and maybe you have the beam resolution that convolves with the image. Is it relevant for the depolarization, or from your models you see the polarization degree going down because of the resolution effects of the telescope?
That's right, yes. Yeah, but supposedly magnetic fields are surrounding the whole the whole black hole, right? It's not like they're only on one side and there's nothing on the other side. They're probably there, and yeah, I think the general idea is, like I said, it's some kind of, you know, depolarization probably. I would expect this emission to be also polarized, but, you know, it's somehow visible as depolarized.
Right. And I have also one last question about your models, your GR emitted models. because you said you separated the temperatures of electrons and ions.
Yes, we allow that, yeah.
It's going to be dissipated by, I don't know, magnetic fields resistively or I don't know, viscosity. So at the end, how do you distribute this energy between electrons and protons or the ions? And is it relevant in this environment's conduction, electronic or via ions?
Yes, so we have very simple prescription for this coupling or decoupling of electrons and ions. We introduce some formula where this process depends actually on beta plasma parameter. In this way, we try to capture sort of like a plasma effects that we completely don't resolve in our models. And we just basically decided to simply, make it a function. The coupling is a function of beta plasma. So by changing different parameters, we can couple the species strongly everywhere, or we can decouple electrons from ions in regions with high beta plasma, weakly magnetized, and they are strongly coupled in strongly magnetized region. But it's not like we choose one coupling is better than the other. We have a spectrum of different type of couplings, and we change that by changing coupling parameters, these R high and R low parameters. So we survey some range of these couplings scenarios. So we consider all these different scenarios, not just, we choose one and say that's the correct one. We don't know which one is the correct one, yeah. That's what we want to find out, actually.
Yes, and the heat conduction, is it relevant for your system?
So, well, it's not really certain how relevant it is. I think there are groups that have introduced thermal conductivity in GR-MHD simulations, but from what I know, this effect was minor and it didn't change the dynamics or geometry properties of models that strongly. But I don't know the details of this implementation, and I think in general this topic has not been sort of like explored, at least in context of this source, yeah, or Sagittarius A star source. So. It's not. It's probably a good direction to work on still. There are other things that may be even more important, like resistive MHD effects, right? Because maybe there are some reconnections that are happening, reconnections of magnetic fields that are happening near the black hole. This kind of ideal MHD simulations that I have shown you in my presentation, they don't capture reconnections very well. All reconnection that we have right now are all, numerical reconnections, really. Maybe, many other non-ideal MHD effects are important. Maybe the thermal conductivity is not the only effect that is important, right. Yes.
I think that has another question, but I will make a very short question before. About when you explained the first part of the presentation about the reconstruction, if I understood correctly, the reconstruction of the projected magnetic field from the polarization maps, right? And you told us there are like 5 different methods and they give us some slightly different results. Is it possible, I don't know, to gauge this reconstruction method using your models or?
Yes, and that's what we have actually done. So I showed you the synthetic images. We convert 2 of them. The 2 first one were actually based on MHD simulations, polarimetric maps from MHD simulations. This was said. I didn't say that, but it was on the slide. So we have actually done that. Yeah. So they have been gauged, and in our publications, the 2 publications that we have published in March, we actually explain this extensively, this extensive description of, all these tests and how each of these 5 methods, performs given this complex models. So, they do recover the models.
Great. Thanks a lot.
Not precisely, but you know, more or less.
Okay.
The satisfactory quality.
Right. And I think we have a last question by Elizabeth.
Monica, it's me again, Elizabeth de Gouveia.
Yes, hi.
Okay.
Yes.
So we, with regard to this asymmetry in the polarization, I thought that, as Reinaldo commented, I thought that this was because the asymmetry we could see already in the intensity maps of 1 year ago. So I thought that you guys had already incorporated some kind of a asymmetry or tilting, slight tilting, because it's not a perfectly face-on source, right?
Yeah.
And then
Yeah.
this might explain this asymmetry in the polarization distribution. Isn't that so? Am I correct on this? Or
you might be correct. I just don't have an answer for that. I think that, yes, indeed, that these models are not exactly face-on. They have slight tilt, and indeed, total intensity drop on the north part is due to, you know, the tilt, right?
Right.
If you see it exactly face-on, it would be ideally, nicely. Maybe it will happen the same for the polarization. I'm not sure.
Yes, maybe.
Though.
You know, these depolarization effects might be intense in one side or more intense in one side than the other one. And but also I have another question with this regard, because it called my attention that some of the ALMA results were very different from the other telescopes. Why is that so? This is one question.
Which one?
Yeah. I think it was circular polarization, but I'm not sure. And you showed that map with the spreading of the percentages, and ALMA was the most different contribution in that map as well.
Yeah. Well, so these D terms, these calibration terms are different for each station, so it's okay. ALMA can be different from APEX and can be different from LMT. It's okay.
Right. So
this calibration terms, it's not like there's one term for all telescopes. They're all different, so they will have all different polarization leakage.
Right.
So this is okay. That's okay.
The other question regards the model, the theory itself, because in all those simulations, you assumed some spinning of the black hole, right? I think it's as small as the standard believes in with regard to M87, right? And also
we have several spins, yeah.
Right, but what was the range that you assumed? Never something very high, isn't that so?
We go up to 0.9475. This is the highest that we had. I think we even have higher in the library, but I'm not really certain if we considered. I think in the library, the highest spin that we have is 0.98.
So what was the most constraining value for this parameter, the spin of the black hole A? And also because your model showed that mainly in the ADAF picture, the MED would be and then this implies small accretion, at least in this phase that we are looking at M87, right? Small accretion rate, MED, and the poloidal field as well, right? Because there is this dominance of the poloidal component. So this would be more or less the overall picture, right?
Just 1 second, Monica, I have to go. Thank you very much for your colloquium. It was amazing. I will catch you on some other opportunity.
All right, thank you very much for the invitation. Yes. So Elizabeth, going to your question, at the moment we don't have a spin determination. We find models with 0 spin that being equally consistent with the data as models with high spin. So, so we don't have yet constraint on the spin. And you know, in our models, the parameter range is sparsely covered. So we have spin 0, spin half, spin 0.7, and spin 9.9, and then nothing in between. And you know, the maximum was like 0.9 something that we went.
That's true.
So you know, we want to be honest. We rather do not want to say anything about the spin, because you know we don't cover the parameter space well enough to say anything certain about the spin. Plus, as I said, this polarization is quite sensitive to plasma effects, this Faraday rotation stuff.
Yeah.
That could be more, has more impact on the image than the spin itself.
And also, one thing with regard to reconnection, because we have been doing GRMADD simulations of ADAF like and with the reconnection to check reconnection. And actually, this is you know, the turbulent component has to be high, and then this may explain also this depolarization and this low intensity that you get for the, because we are not looking at really a coherent component, but this is just, you know, something that maybe, as you said, that there is lots of things to be searched, to be understood. And
absolutely, I just want to say that my main message is that it's not over. It's just the first step, and there's definitely a lot of more work to be done and a lot of more to understood, and we have more data. So that will be more informative if we, you know, do this study. It's not only on longer time scale, not 4 days, but 2 weeks. But also, you know, if we confirm we want to do this every year, this observation, so we know we have more data now, maybe based on this long-term evolution, like from year to year, or within 5 years of observation, we will be able to tell more. But, you know, we still have to analyze this data. There's a tons of data waiting to be analyzed, and that will take time. Yeah, but, you know, hopefully in the near future, like within 5 years, we will be able to say way more. Both on conditions of plasma, evolution of the source, but also hopefully on spin. I think that's like a holy grail in this area now that we really want to measure the spin. That's true. We measure the mass, now we want to get the spin.
And let's see what very high energy bands can tell us about in the next few years as well. I mean,
that's right. Yeah, and we do these observations also together with Fermi, Chandra, and all other possible facilities whenever they can join. We do, you know, EHT together with all the multi-wavelength campaigns. So yeah,
it's rather important. Yes, this synergy.
Yeah.
Great, Monika, and thanks a lot for, you know, this seminar to us.
You're welcome.
Take care.
I thought that was the last question, but I think Juan has also one question. Is it Juan? I wasn't sure.
I think it was just left over, maybe.
I wasn't sure if he forgot the...
I think he forgot it, yeah.
Yeah, okay. I think he's not there. So we can finish the transmission now. Would you like to thank again, Monika, for the very interesting seminar, for all your time and knowledge you shared with us, and also would like to thank everyone participating and attending this seminar. And I think, Alexandre, we can finish the broadcast.
Thank you, Monika. Thank you very much.
You're very welcome, and thank you so much. Obrigado again for coming.